All right, guys. Hello. So last week we started talking about an introduction to optimization concepts, and we also started talking about how we can actually fit a model to a set of data points. Okay, and we discussed that if we have uh, a number of variables in a model, okay, for example, okay, let me just make a quick introduction, okay, 406, um, least squares, continued. Okay, continued, sorry, squares, continued. Okay, so we basically started talking about fitting a model to a set of points, and we basically said if we have, let's say, a relationship between x and y, okay, and you have basically, let's say, 2 points, and you want to try to find the best fitting line to these 2 points, essentially you get a system of equations in terms of x and y, and also this line, right, this f of x has a parametric form, alpha 1x plus alpha 2. Alpha 1, alpha 2 are unknowns, and basically finding them is the problem. And if you have just 2 data points and 2 unknowns, this basically gets transformed into a times alpha is equal to b, okay, where basically a and b are from the data points, and you get alpha being equal to a to the power minus 1 times b. And A is a square matrix in this case and is invertible, or as long as it's invertible, we have a solution for alpha. Okay, and we have also discussed when A would not be invertible. For example, in this example, if x2 collapses to x1, so that these 2 data points become 1, essentially the matrix A becomes singular, and therefore we cannot invert it, therefore we cannot solve this problem. Okay, so when do we have a problem with inverting A, right? One is that basically data points collapse, meaning that basically A is singular. Example, right? x1 is equal to x2. Okay. Another common problem is we have more data points than unknowns. Okay, too many, that means too many equations in terms of alpha 1 and alpha 2. Too many equations in terms of alpha 1, alpha 2. Okay, this we usually call an over-constrained system of equations. Over-constrained means you have just 2 free variables, 2 degrees of freedom in a sense, but you have more than 2 equations that constrain those 2 variables. So you end up with no solution for that system of equations. Okay, so this means you have 2 or let's say, too many rows in A is not square, and therefore hence not invertible. Okay, remember that in your A alpha is equal to B, what you have is basically that each data point essentially results in a row in this equation. Okay, remember this is just alpha 1 and alpha 2, and you have basically the B matrix. Each equation essentially fills one line, one equation fills one line of that matrix equality. Okay, so in this case we have A being an m by n rectangular matrix. Okay, remember here I have n variables and I have m equations. Okay, and therefore B is an m by 1 matrix. Okay, it's a column matrix essentially. So that's our problem, right? We cannot invert A, therefore we cannot write down alpha 1 and alpha 2 in terms of the known parameters or known coefficients in this equation. Okay, so how to proceed, right? How to proceed? Conceptually, right? It's a good thing to have more equations because, or let's say it's a good thing to have more data points, but you need to switch your approach in terms of how to approach the problem, right? Instead of just trying to have a perfect fit, let's say a nonlinear equation, let's say these are your data points, right? For each xi, you have a corresponding yi. What you're trying to do is basically find a best fitting, in this case, best fitting line or a curve. Okay, let's call this f star of x, and this is our x. But you see that you cannot go through all the points. Okay, especially if your number of variables in f of x, the number of parameters in f of x is less than the number of data points. So you have an approximate model or an approximate fit. Okay, so this now is an approximate fit to the data. Approximate fit to the data. You see that in each data point, there is an error between what the curve says and what the data point says. Okay? So, simply, we cannot give up. We need to formulate this. As an approximate solution. Using the optimization concept. Okay, so remember what optimization was. Optimization is that you define a function of a number of unknown parameters, and you are asking the question, what should be those parameters such that this function is minimum or maximum. Okay, so the ultimate question is, how can we define an objective function? remember, we need to define an objective function such that if we maximize or minimize this function in terms of the unknowns, we find the solution to our problem. What are our unknowns? Our unknowns, in this case, for example, for a line fitting problem, is this alpha 1 and alpha 2, the unknowns of the linear function. Okay? So how can we define an objective function such that if in this case, we will minimize it, such that if I minimize this function, I find the best fitting alpha 1 and alpha 2. Okay? So the idea is to define an error function and try to minimize that error. When I say try to minimize that error, what I mean is try to find the alphas that would lead to the minimum error. Okay, so these concepts are very general, and if you think about many problems, defining a proper objective function is an important part of that problem, and essentially trying to define some kind of an error is an important part of that problem. Okay, so how can we define our error? Remember, we seek actually a solution to A times alpha equals B, which we cannot solve. So what we can do instead is transform this into A times alpha minus B is equal to 0. Again, something that we cannot solve. But how can we solve this equation approximately? Well, if this is equal to 0 in the ideal solution, what we can do is, can we minimize this? Okay, because if we minimize it, it's going to be as close to 0 as possible. Okay, so we define the error as this difference, okay, A alpha minus B or B minus A alpha, okay, where this error actually is a vector, right? E is an element of Rm. So that means, remember, B is a column vector where you have as many elements as the number of equations. Same with E, okay? M, remember, is the number of equations. So for each equation, for each data point, you actually have an error. So you see this error is actually EI. So this is an error, right? A difference between what the data point says. This is B, okay? So this is the data point. And A times alpha is what the function says. In this case, the linear function. Okay? So EI is the error of the ith data point. Okay? So it's a vector, basically. Note, if A alpha equals B had a solution, the minimum value of E would be 0. That means the function actually passes through each one of the data points. This is only possible if, remember, if the number of variables is equal to the number of data points. Okay? Now Now, here comes the name for the least squares, okay? Least squares term, okay? Where that comes from. Now, let us define the mean squared error. Squared error. What is that? Well, we define the error, but for us, the sign of the error is not very important because we just want to make the error as small as possible. So we want to get rid of the sign of the error because we don't care. And also we want to make the error function differentiable. Why is that the case? Because remember, in order for to apply the necessary conditions, we need to take the derivative. So we need to find an error function that is irrespective of the sign of the error, and also it's very easy to take the derivative of. Okay? So therefore, we define a total error, which is basically over all the data points, e equals 1 to m, and the square of each error point. This is a mean because the only thing that needs to be to make this a proper mean is basically to divide to the number of data points, but we don't need that because we will just essentially minimize this function. So we don't care about its absolute value. Okay, so what is this? This is E1 times E1 up to EM times EM. Okay, this also can be written as a matrix multiplication. Okay, in fact, so it is E1 up to EM, a row vector which is multiplied by the same vector but in column form, E1 to EM. Okay, so in linear algebra this corresponds to a transpose operation. So this is E transpose E. Okay, this is the matrix transpose. So what is this? This is actually this is the squared norm, squared, in fact, Euclidean norm of E. Okay, squared Euclidean norm of E. If you think about this as a vector, it's actually the square length of that vector. Okay, so we can also write this as with this notation. Okay, this is norm of E squared. Basically, more on all of this in EE 501, right, which is essentially covering advanced linear algebra. Okay, so how do we solve this? Okay, there are different approaches to solve this. Okay, different approaches to solve this problem. Many, elegant concepts in linear algebra. Again, many of you will take EE 501 to cover all of this, like, for example, range space of a matrix, range space, null space, orthogonality, etc. I will not cover these, but essentially what I will cover is essentially a solution through calculus. Okay, another solution through calculus. Well, the solution through calculus is actually through these necessary conditions that we have we have discussed. Okay. All right, so let's recap what we are trying to do. We are trying to find a best fitting model or best fitting function to a number of data. The number of data points is more than the number of parameters in the function. And therefore, we have an over-constrained or over-determined set of equations that we cannot directly solve. So what we are trying to do is define an error, use optimization to minimize that error, and find the alphas, the parameters that actually minimize that objective function. All right. So we have J of alpha, which is equal to the error squared. Okay, in fact, let's do it this way. Yes, the error as a vector squared, and that is equal to what was our error? It was A times alpha minus B squared. Okay, and we have already written this as A times alpha minus B transpose times A times alpha minus B. Remember, A is a matrix, B is a column matrix, alpha is a vector. A column matrix is nothing but a vector, obviously, right? So we can expand this. So this becomes, when you take, by the way, note, if you have two matrices A, B transpose, it is equal to B transpose A transpose. Okay, so therefore, when I take the transpose of the inside, what I have is alpha transpose A transpose minus B transpose A times alpha minus B. Let's expand this. So we have alpha transpose A transpose A alpha as the first term over here. Now the second term minus alpha transpose A transpose B minus B transpose A alpha and plus B transpose B. Okay. Now these two terms are one by one matrices. Okay, scalars. Why is that? Well, take a look at the sizes, right? You have alpha transpose being, remember, alpha was n by 1. So this is 1 by n. And A transpose, A was actually m by n. So the transpose is n by m matrix. And B is an m by 1 matrix. So this leads to a 1 by 1 multiplication. Remember, the multiplying dimensions should basically agree in order for the multiplication to be possible. And as a result, you have a 1 by 1 matrix in the end. So these two are scalar numbers. So what I can summarize this with is that this becomes basically 2. Okay, so this becomes alpha transpose A alpha minus 2 times B transpose A alpha. It doesn't matter which one you write down, B transpose B. Okay, so now let's use our optimization concept. Okay, so necessary condition for alpha star to lead to the minimum of J. Now let's also take a look at what's happening here. This is a quadratic expression. You see, it is a square in terms of alpha. So I have alpha transpose alpha, so it's a square of alpha in a sense. So that means it's actually a quadratic function. It's like a multi-dimensional bowl, okay? Because A transpose A is positive, okay? So if this is positive definite or semi-definite, this is again a concept from linear algebra, okay? Basically what we have is like a bowl, a multi-dimensional bowl in alpha space, okay? So a quadratic form. Global minimum. It has a global minimum and we need to find it, okay? So what was our necessary condition? So what we do is we take the derivative of J alpha with respect to alpha, okay? So what happens is that we are doing this in terms of a vector notation. So that means in reality we are taking the derivative of J with respect to each alpha, and we get a set of equations from those. But we will do this in matrix form, okay? But you can verify this, let's say in a 2 by 2 matrix with alpha 1 and alpha 2, and and you can verify that these matrix equations hold, okay? In this case, you see there is a quadratic term here. When we take the derivative, it's going to be equal to 2 times A transpose A alpha, right? And in this case, I'm basically letting alpha be alpha star, because when I solve this, I will be finding, this over here, the alpha star that leads to this minimum value, okay? Minus, you see there is only alpha here, so I have 2 times B transpose A or A transpose B. It doesn't matter here. Actually here. It actually doesn't matter, but let me use it here for consistency with my later. Let's use this term, okay? A transpose B. Okay? So 2 times A transpose B, and that's going to be equal to 0. And we need to solve this, right? So let's cancel out the constant term. So I have A transpose A alpha star. A transpose A alpha star is actually equal to A transpose B. Okay? Now, A transpose A, remember the size of A transpose A, right? It's an n by m times m by n matrix, and therefore it's an n by n matrix. Okay? So it's a square matrix, and although we will not attempt that, A transpose A is non-singular if A has a column rank of n. That means at least A has a number of independent columns. Okay, all columns of A are linearly independent. So proving that A transpose A is actually non-singular if you have linearly independent columns is actually not very easy with the current given knowledge that you have, but it's a topic again of EE 501. Okay, but remember what that means. Okay, it means that you have at least, for example, for a line fitting problem with two variables, you have at least two data points that are not collapsed to each other. Okay, if you have two x's being the same, then you have the column rank of A being 1 instead of 2, and you basically have infinitely many solutions. You cannot in that case have a non-singular A transpose A. Okay, so so in your case, I guess it's sufficient that you check that A transpose A is a non-singular matrix. That means its determinant is not equal to 0. Okay, if A transpose A is non-singular, we have alpha star being equal to A transpose A inverse, because we take the inverse of A transpose A, multiply from both sides with the inverse. On the left hand side you have the identity matrix which we can eliminate, and then on the right hand side you have this as a remaining. Okay, now this new matrix over here that multiplies B is often called the generalized inverse of A. That means if A is not a square matrix, but you still want to invert it in the so-called least squared sense, you talk about this generalized inverse of A. Okay, so alpha star is equal to this generalized inverse A transpose A inverse A transpose times B. Okay, all right, so now I know that you know, these are kind of don't be kind of panicking. Now these are all in terms of matrix algebra. It really is an introduction to linear algebra in 501, where you will cover all of this. Okay, but essentially I will illustrate all of this with some examples, some numerical smaller dimension examples, and hopefully those will be much more clearer. Okay, so I will proceed with an example. I will break the video here and proceed with the example in the next video. Okay, but we will continue with these notes. All right.